to the 5th tutorial in this series on trigonometry. Now, in the last tutorial we looked at the sine rule, which is a very useful way to calculate lengths and angles in triangles. It relied though on you must knowing an angle and its opposing side. If you are given information about the triangle but not an angle and its opposing side, then you can use a different rule called the cosine rule, which is slightly unwieldy, I have to say, but still very useful. And it can be derived, but not in such a simple way as the sine rule, so I'm going to skip a derivation here, but I will motivate it for you by sort of comparing it to Pythagoras' theorem, because it looks a little bit like Pythagoras' theorem. So let's have a triangle, again, a common or garden triangle, nothing special, no special features, just a common or garden triangle here. And let's label it in this fashion. Those are my three lengths, and then I'm labeling with vertices here with capital letters. Now, let's imagine that you were given this angle, C, and let's imagine that you were also given the lengths A and B, but you were not given the opposing length, so you wouldn't be able to invoke the sine rule. Then the cosine rule is a way to calculate this opposing length, and let me just quote it for you. It says that the square of this opposing length is the sum of the squares of these two sides, and that sounds very Pythagorean, doesn't it? But then take away twice the product of those two sides multiplied by the cosine of the opposing angle. And you can see what I mean about this being a slightly unwieldy formula compared to the sine rule. But it is what it is, and it is very useful. It's sort of connected to Pythagoras in the sense that if we rotated this point round such that C was a right angle, then we would stretch out this length C. Maybe I can sort of sketch this actually. If I kind of rotated this point round here, then C would be a right angle, and the length C would be this stretched out length here, and it would just be given by a squared plus b squared if I had just rotated that length, okay? But obviously in the triangle we have, the length C is smaller than that imaginary sort of hypotenuse there, and this term is like a correction then. It gives you the correction to Pythagoras' theorem in the case that this angle is not 90 degrees. So that's one way that you can think about the cosine rule, which demystifies it a little bit, because it, as I say, it's a rather ugly beast, I would say. So let's just use it to do an example. So let's take a triangle. Let's say this angle here is 50 degrees. Let's say the adjacent sides are respectively 3 units and 5 units, and then we have to ask what's the length of this side C opposite to the angle. And we just plug in the numbers really. So the square of this would be the sum of the squares of these two sides, so it's 3 squared plus 5 squared. Take away twice the product of those two sides times the cosine of the angle 50 degrees. So this is 9 plus 25, which is 34. Take away 30 times cosine of 50 degrees. And let me just get the calculator to work this out. Just a sort of little technique point here. You could put all of this into a calculator, and I think on modern calculators you can see everything that you're typing in, but I think a lot of marks are lost in exams by students essentially fumbling with their calculators. And I guess my sense is when you have very simple little bits of arithmetic like this, I would just do them by hand. 9 plus 25 is indeed 34, and then I have 2 lots of 15 is 30, and then use a calculator at this point. There's much less room for error. So I have 50 degrees, take the cosine of that, multiply it by 30, and then I want to subtract that from 34, and that gives me 14.7 dot dot dot, and then c will be the square root of that, and I get 3.836 dot dot dot. I'm going to write that as usual to 2 decimal places, 3.84 units. Okay, so that's a very typical example of the use of the cosine rule. Now, an alternative is that you might know the 3 lengths, but then be asked to calculate an angle, and you can actually rearrange the cosine rule to cope with that case. So let's take this cosine rule and just do a little bit of algebra on it. So I have, let's see, I have c squared is equal to a squared plus b squared minus 2ab cosine c, and this will be a good exercise in rearranging equations. Let me take this whole term over to the left hand side. So I have 2ab cosine c plus c squared is a squared plus b squared. Then let me take this term to the right hand side. So I have 2ab cosine c is a squared plus b squared minus c squared, and finally let me divide by 2ab, and you see I've now got the angle, cosine of the angle all by itself on the left hand side. And so this is just the cosine rule rewritten such that if we know 3 sides, we can determine an angle. I'll just box this too, given it's such an important formula. So let's just do an example to see how this would work. So let's say this is the unknown angle C, and let me just label my triangle as before so I don't get confused. And let's say that this length here is 10. Let's say this length here is 8. And let's say we know this length, and let's say that length there is 7. And then the question is, what's this angle, C? Now one has to be a little bit careful using this formula that if you're given all 3 lengths and asked to calculate a certain angle, you have to identify, right, these are my 2 adjacent sides. These are going to play the role of A and B in this formula. So it's the adjacent sides to the angle that you're after that you're going to add the squares to and divide by twice the product of. The opposite side only appears once with its square subtracted. So cosine of C then will be the sum of the squares of these 2. So it would be 8 squared. Actually, let me just write it. This 10 squared plus 8 squared minus the square of the opposite side divided by twice 8 times 10. So this is 100 plus 64, which is 164. Take away 49 divided by 160. So we have that the cosine of C then is 164, take away 49, and then divided by 160 is 0.718 ... And again, just like we saw with the sine, if you know the value of cosine or sine, you then use the inverse function. So c will be the inverse cosine of this number. And you'll find it on your calculator. Here it is, inverse cosine. And I therefore find that the angle C is 44.0 degrees to 1 decimal place. So I hope you found that helpful. That's the cosine rule. As I said a number of times, quite an unwieldy creature, but still very useful for those cases where you do not have an angle and an opposing side, but you do have information such as an angle and 2 adjacent sides, or alternatively 3 sides and you're asked to find an angle. So I hope that's been helpful. That's in the last 3 tutorials we've done a lot of calculating. We've calculated areas and sides and angles using the sine and cosine rule. I want to go back to more conceptual things in the last few tutorials in this series. So we're going to look in the next tutorial at some special values of sine, cos and tan that I think you'll find very helpful. And then I want to use a construction involving triangles inside a circle to motivate what do sine, cosine and tangent actually look like as functions of an angle. And that opens up the whole sort of beautiful world of the mathematics of the function sine, cos and tan, which is truly a remarkable world and so useful in both maths and science. And then we'll end this series by solving, as I say, some trigonometric equations. So these are algebraic equations involving sine, cos and tan, which is quite a tricky topic, and we'll probably spend 2 tutorials going through different ways of approaching that. So I hope you're finding this series on trigonometry helpful, and I'll see you next time.